So here's a view of a sketch of the umbrella by Candela, and you see that below ground, the foundation is an inverted umbrella that cups the earth. And this is an important foundation in his designs also, because if we think about Mexico City, there was a significant earthquake in 1985 where many structures collapsed. It was a real significant earthquake, but as far as we can tell, all of Candela's structures not only didn't collapse, but they still remain in excellent condition. And the inspiration for Candela for this umbrella was a paper that he read as a student by Ayman in 1936. So while he was in Madrid, he read this paper where he sees this umbrella structure, and it gives him this idea when he's in Mexico. But you can see the difference between what he saw and what he did. And the difference is something that is shaped and proportioned by an artist. So for example, we see the column on the right was short and a fat column, and we see those stiffeners on the edge of the shell that thicken as it goes towards the valley. And these are all perfectly rational engineering designs. But what Candela did was he made the column taller and more slender, and he made that edge beam the same thickness. He's still adding steel. It still has the correct amount of strength. But you see a different kind of proportioning from the basis of his inspiration. And by placing many of these umbrellas side by side, he could create large roof coverings. So here you see the Rio's warehouse, and by tilting that umbrella, light enters the space. So where you see the sawtooth right here, that's where you'd have windows letting light enter that space. So Rio's warehouse, for example, cost 50 cents per square foot, and at that time that was half the price as if the more traditional warehouse of, say, steel with corrugated tin roof type of construction. So it was a very economical type of design. He'd have 4 sets of umbrellas being constructed at once, 4 form boards. 1 week later, he can decenter that formwork, build another 4. So this whole project was complete in just 3 months. So by 1960s, the early 60s, he was designing around 30 umbrellas per week. And around that time, Mexico City had about 3 million square feet covered with these umbrella structures. So this was, as I said, his bread and butter for his firm. But before he would actually build for a client, he was experimenting. So here's one of his experimental umbrellas in 1953, where after the umbrella was decentered, all of his workers stood on top for a photo op. And what he was learning here was the proportion of the umbrella. So he was looking at that rise, the rise to the projected area, plan area. And from this experiment, he learned that the tip of these umbrellas were deflecting too much. So he needed to increase that rise. So through this kind of experimentation, he was optimizing the form of these umbrellas. And so what we did was we took some of his designs, and we ourselves started to look at the optimized rise to area ratio, where this is a plot of the downward deflection at the tip versus that rise to area ratio. Candela identified 0.015 as his target around their rise to area ratio, and the circles represent the as-built designs of Candela's 5 structures. The other points represent our analyses to show how that would perform if we changed that rise to area ratio. But he also determined that the optimal area of an umbrella should be no more than about 2,000 square feet, because that's based on restricting the height, which if you increase the height any further, then you have too much volume in that space. And so now we're talking about energy efficiency. So he also had this idea of energy efficiency, where it would be then too expensive, for example, to heat that space. We also looked at optimizing the thickness. So if you look in plan at these umbrellas, he thickened the valleys, which is perfectly right, because you have the stresses from the shell and the quadrants moving towards the valleys, and these valleys are acting essentially like cantilever beams. So there's a lot of reinforcement that goes into those valleys. But we use a modern structural optimization tool, which looks to optimize the distribution of the thickness to decrease the deflection at the corner. And that optimization is indicating that the optimum place for that extra added thickness was in these locations here. So maybe a diamond-shaped pattern of increased thickness would have been a more optimum solution for decreasing the deflections on the corners.